3:30, that's my signal. We're ready to start. So, as I promised on the lecture on Friday, we're going to go back to reviewing a little bit information theory because we went through the concepts in 2 seconds. We don't really need information theory in any significant way in this class, but there are some concepts that actually you get much appreciation of what they mean by having a course on information theory. And my understanding is there is such a course in EE, right? So some of you must probably have taken already that course. But I'm also going to give you an online course by David Mackay. Both his lectures, video lectures, and his whole book is available free on the web. So if you have time, either in the context of this course or later on, maybe you can take a look on that. Okay, so always very ambitious in the lectures. I put too many topics. If things don't work out, the final posting, I will start cutting things, okay? But literally, most of the second half of the lecture today are things we already have seen, sort of, okay? Now, I understand there is a lot of material there for those who are new to this type of topics, and that's why I need to start giving you a homework set, because I understand that you look at the equations, they don't mean anything unless you have to do something with them, and to do something you have to do homework, okay? I don't want you to memorize anything, but I want you really to feel the need of going back and forth in the notes, looking for things that may be useful to the homework. So I'm going to start giving you the first homework in pieces before Wednesday. So if you look on the web back by tomorrow, you will see homework there. Okay. So as I told you, the book, Information Theory, Inference, and Learning Algorithms is available online. David Mackay was one of the pioneers on Bayesian inference, neural networks, and many other things. His video lectures are available from Cambridge. So it's, I think, maybe 15, 20 hours long video lectures. So you can consult those. Okay, so I'm going to give you a very superficial view of information theory, emphasizing maybe 3 concepts that we will see them very often in this course. So information theory is basically concerned with the way we transmit and compress data. And our data, of course, come from some probability distributions, so that will come to be relevant to the type of things we're talking today. I already mentioned in passing last week that when we're going to compact in transmitting data, we have to do it in a way that we allocate what is called short code words to things that they are very probable, and very long code words on things that they are less probable. And a typical example of this is in natural languages, for sure in English, where very often used words are very small, like ev, v, and, etc. And things that you don't use very often are very long words. Now, I want to believe that this is true in every language. So if you know a language where this violates that, let me know, because that will have an implication on how rapidly that society has grown up, where these rules basically don't take place. Okay. So we want basically to have some measure of quantifying what is called information, and we can use the interpretation of degree of surprise when we learn some new variable, the value of some variable x. So what is the degree of surprise on learning that? So obviously we want this to obey the following. If this value of x is highly probable, all right? Highly probable, is that a degree of surprise? Is it high or not? If it's something that's going to happen 99% of the time, do you learn anything from it? No, so we need a measure that says basically that that's the case. And also we need another very obvious statement here, that if we observe two values of two variables, let's say x and y, that they're independent of each other, what we learn by observing both x and y should be basically the sum of a of x plus h of y. And a good way to come up with a measure of what h should be is to look at the probability of two independent events, p of x and y being p of x and p of y. So can we make this equation sort of to come up with a proper definition of h from this equation? And the answer is yes. And so we define this degree of surprise or information that we gain when we learn x to be minus the log with the base 2 of p of x. So it satisfies the two desired futures for h of x. And for us, we're going to define entropy as the average of this measure with respect to the distribution p of x. So this is the definition of the entropy of x for discrete events. And you can extrapolate, and we will see the equation again. For continuous events, this will be, the summation will be an integral of p of x log of p of x. And usually the units for the log is, the base is 2. So that's what we will use here. So here is one example, and actually let me stay on the top. If you have a uniform variable that takes, let's say, 8 possible values with probability 1 over 8, so the entropy is 8, so you have basically 8 states to sum over, the probability 1 over 8, the log of 1 over 8, and this comes equal to 3, and the units we measure this is bits. Okay? If we have another variable with 8 possible states, but the probabilities now are not equal, they are, let's say, from 1/2 to 1 over 64, so from something that happens 50% of the time to something less probable. So the entropy will be calculated with the same formula, but also on this table, I give you, in addition to the probabilities of the different states, I give you the code words to represent each of these values A, B, C to A's. And you notice less probable words have very long code words. Something very probable has basically, you only need code word of order 1 basically to describe it. So if we sum these things up, the entropy for this comes to be 2 bits. So not surprising that the uniform distribution has the maximum entropy here. This is less than that. Okay? And there is a theorem that you learned basically on lecture 2 or 3 when you take information theory. And it says that the entropy is a lower bound on the number of bits needed to transmit the state of a random variable. Okay? This is the main paper of Shanon on information theory. Now, physicists have a different definition of entropy, that it comes out sort of to be equivalent. And because I think we have 3 or 4 physics students in the audience, let me just say in passing what that is, and this is very much related with entropy as well. So let's say that we have n identical objects, let's say spheres, and we are going to place them in different bins, and in the if bin we're going to place ni objects, ni spheres. Now you can think that the way you place them, you really count which one you place first, second, third, fourth. So really on bin I, the variations of the different arrangements that you can get is ni factorial. So the physicists, the way they define entropy is basically with the multiplicity of the different microstates that you can get. And that is defined by n factorial divided by the product of these arrangements on each bin, which is ni factorial. I am not going to do the algebra, right? But if you assume n to be very large, and you use the standard approximation for the log of n factorial, which goes under which name? Which formula is that? No, this is a very famous formula that we will use many times. Log of n factorial and log of n minus 10. Stirling's formula, okay? So remember, this is very useful. So when you plug in things and you take the limit n going to infinity, and you define ni over n to be this probability of the microstate I, as we call it, you basically get the same formula as we have defined from information theory. So the two things are sort of equivalent. So in statistical mechanics, you will see people defining entropy this way, but they are practically the same things. Okay. So two examples. Something that distribution that looks picked, it has lower entropy. Obviously, that's something that is widespread and less uniform. We discussed about the maximum entropy for a discrete distribution, and I'm going to give you actually later on a very nice cute proof that the uniform distribution has the maximum entropy. But right now, the way that I saw it on this slide is by maximizing the entropy with the constraint that the sum of all the pxi's is equal to 1. So I use a Lagrange multiplier. We will do this often in this type of calculations. So if you do the algebra, it comes up that for a discrete variable with m states, the entropy is log of m. So every discrete distribution has entropy less than log of m. Okay? So you get the log of m. You can see this is 1 over m. So there is summation on m variables, so the two m's cancel out, and basically you get log of m. Okay? So this has the maximum entropy, and basically the derivation is by maximizing what you see on the top. And actually, I mentioned I'm going to give you another proof. It's on the bottom, but I'm going to come back to this later on when we discuss about a very fundamental inequality in probability theory. So I'm going to come back on this proof on the bottom. Okay. We don't need this. This is too trivial. So if we generalize this to continuum variables, basically you can come up with a definition of entropy by sort of taking a continuous distribution and splitting it in pieces over bins, right? And then taking the length of these bins to go to 0. And eventually what you get is the entropy for the continuous variables is minus p log of p dx. So if you have continuous distributions, the maximum entropy distribution is a Gaussian. And what you see on this slide is a proof of that for univariate Gaussian distributions. And the only thing I want you, I really want you to read this and sometime spend maybe 10 minutes to do these derivations, because there's much to learn, okay? So this is, we want to maximize this, but we maximize this with the constraint that p is normalized, right? So integral of p is equal to 1. But also we take the constraint here, so we can compare things with the Gaussian distribution, that the mean is equal to mu, and that the variance is given equal to sigma squared. So the way you do this is you use 3 Lagrange multipliers to enforce the constraint, and rather than maximizing h, you maximize this h curly notation here, this expression that you see here. And you use calculus of variations. And I would like to assume that this is not new to you, right? If it is, when you take your math course in the first year and the professors don't cover calculus of variations, start screaming. Okay, and I mean it. Because it's sort of fundamental problem. So basically the idea here is you are going to maximize this, but with respect, okay, it's a probability, but you can think with respect to a function. And so you have to set the function of this equal to 0, and usually the way you do this is using variation, perturbation to that function, and setting that perturbation equal to 0. Okay? Setting basically the directional derivative with respect to p of x equal to 0. If you actually look at this expression and that, you will say, I guess, common sense, all right? And if you feel comfortable, that's great, it's common sense. If not, you will have to read a little bit more about calculus of variations. So anyways, if you maximize this, you take the derivatives also with respect to lambda 1, lambda 2, lambda 3 to satisfy the constraints. It comes up that the maximum entropy distribution, the invariant one, is the Gaussian. And I give you the result here for a multivariate Gaussian as well. I think later on in the slides I give you the proof for that as well. Okay. Interestingly enough, it comes up that the entropy can be, for a Gaussian, can be less than 0 for certain values of the variance. Okay, so that don't be surprised with that. All right. Now, one of the most fundamental definitions for everything in this course and everything course in machine learning and Bayesian inference, and that is the Kullback-Leibler distance between two distributions P and Q. There is an information theoretic sort of definition that I'll give you here, but I'm going to go directly to why we need this and what it says. Okay. So let's say that you have a distribution P that is either very complicated. Yep. For the relative entropy. The negative entropy, remember that entropy actually, I'm going to show you shortly, when I do the derivations, anything that is constant doesn't mean anything. So if it is negative, you can switch it and make it positive and it won't make any difference. So where you measure 0 doesn't mean anything. Okay? So I'm just saying, if it comes to be negative, don't panic, because that reference, it is not relevant. We're going to be comparing entropies between distributions rather than using the absolute value of a distribution. And I will show you actually shortly where I will start dropping terms in the entropy calculation. Okay? So the Kullback-Leibler distance, so P can be a complicated distribution, and you want to approximate it with something that is easier to work with. An example would be you have some distribution that it's implicit maybe, and you want to approximate it with a Gaussian, and you're asking yourself, what is the mean and the variance of the Gaussian that this approximate distribution Q is very close to P? So the measure, this Kullback-Leibler measure is this integral for continuous distributions of minus P ln of Q over P dx, okay? If you expand it, you have minus P log of Q, which looks like entropy, but is what we call cross entropy. So basically, the idea here is that the actual distribution of X is P of X, but basically you code it with an approximation Q of X. So it looks like entropy, but P and Q are different. Now, this is called distance, but it doesn't satisfy all the requirements of a distant metric, okay? And maybe the last 10, 15 years, especially in network theory, there have been many more generalizations of this distance, because it comes up that this KL distance doesn't work properly for network problems, okay? So you may hear things about transportation norms and the like, but certainly you cannot avoid knowing and working with the KL distance, because it comes up practically everywhere else. Okay, so the KL distance, and I'm going to show to you somewhere down the slides, it is greater or equal to 0. It's only equal to 0 when P equal to Q. And importantly, it's not a symmetric distance. Well, you don't know any other distance that is not symmetric, do you? I mean, if the distance of one of you from me is different of my distance from you, that doesn't sound very reasonable, but the KL distance is not symmetric. And you do actually get different sort of algorithms, as we will see later on in the course, if you use the distance of P from Q versus the distance of Q from P. And actually you get some very useful algorithms, okay, but the distance is not symmetric. You can, and this has been tabulated in books, maybe even if you search it in Wikipedia, you will find, if the distributions P and Q are, usual distributions, like for example, if you have two Gaussians, the KL distance can be written analytically in terms of the means and the variances, all right? And actually, you can do the same thing for two multivariate Gaussian distributions. If you know the means and the variances, you know this is what the distance is. And again, these formulas will be very handy when we work with variational approximation methods. So when you do come up with the distance between two Gaussians, you know immediately what the answer is going to be, and you can use it. Now, if you ever see any mistakes on the slides, and there are infinite, because every time I look at them, I find 50 more, please point them to me, okay? And lots of them have been corrected the last 2 or 3 years, but if you see, you know, that this minus sign, you come up to be plus, first, before you email me, double check to be sure that you know what you're talking, and then send me your proof and I will change it, okay? Because sometimes when you do the proof for the first time, you miss signs, so we'll appreciate any corrections. All right, a very important inequality that is used to simplify basically calculations. You know, lots of times, if some expression is very complicated, you use bounds to manipulate rather than the actual expression. And Jensen's inequality is the most often used inequality in probability theory. So let me just give you this with a picture. There's no need for a proof. What you have here is the convex function, okay? So basically, if you take this straight line between A and B, all right, which are, so this is f of A and this is f of B. If you take any point in this straight line, the value of that point is bigger than the value of the function at this intermediate location between A and B. So this expression that you see here is effectively the definition of convexity for this function. Okay? In the slides, it doesn't take it like that. It says, well, if this is true, then the function f is convex. And if the function is convex, then this is satisfied. Okay? So for convex functions, this is a very important inequality. So let's see how it's going to look like in probability. So in probability, what I'm going to do is I'm going to start with a discrete random variable. So I'm going to make lambda I to be the probability of event I. So look at this summation. If you have a random variable that takes m values, summation in I of p of I times f of xi, isn't it the expectation of f of x by definition? Right? So this right-hand side becomes the expectation of f of x, and on the left you have f of the expectation of x. So this is a wonderful inequality, and it's valid only when f is, when it's convex, okay? You won't be able to use it otherwise. Now, if f is not convex, but it's concave, can you use this in some sort of way? So if f is not convex, but it's concave, what can you do with this inequality? You use minus the function, and indeed, what is? Well, I am saying it here. Let me see if it's on the next slide. Nope. So let me just, don't need this. I'm going to come back because I have an example on this, okay? All right, well, let's actually, I told you I was going to tell you an application why the KL distance is greater or equal to 0. Here is an application of the fact that we have this Jensen's inequality and log is a concave function. So look at this very nice one-line proof that the KL distance is greater or equal to 0. And the argument that I'm using here, this is, you will see it many calculations in machine learning. So the definition of KL is minus p log of q over p dx, all right? Remember, minus log is convex. So isn't it this the average with respect to p of the function, which the function here is log of q over p? So can I write this greater or equal to minus, now the function goes outside, log of the average P of Q over P of the argument. P and P cancel out, and Q is a distribution normalized. Integral of Q dx is 1, log of 1 is 0, so KL is greater or equal to 0. So that's a nice, cute, basically proof that the KL distance is greater or equal to 0. But again, this reversal of the log from inside this integral to outside is what is going to make life very easy in very complicated calculations. Okay, I am using it actually here for discrete distributions for another proof to show you what we stated before. For any distribution, discrete distribution, the entropy is less or equal to the log of this size of the discrete space, right? We call it M before, and there is a simple proof again with the KL distance being greater or equal than 0. This slide is a little bit off maybe for for discussing it, but I wanted to show it to you because it is something that comes up in research publications quite often, and it is something that connects the KL distance, or KL divergence as it is called, with the maximum likelihood estimate that I mentioned it in passing in the last few lectures, and I'm going to come back to it in more detail. So let's see what this link between maximum likelihood and KL distance is. Suppose you have a distribution P, and you try to approximate it as before with the distribution Q, but the distribution P is only known through some samples. So the distribution P maybe is a computer code, and you can draw some samples, but you don't really know P. Okay? So I want to approximate Q, and I want to use the approximation Q of P where P is known through this sample success. All right? So obviously, the only approximation I can do is minimizing this KL distance. So I am going to use the definition of KL divergence. And P is known through the samples. So I have to approximate this integral using a P what? If you have a distribution, I mentioned in passing, right? And the only thing you know are samples of the distribution. What is the approximation we can write with these delta functions we were talking? How can I write P approximately if I only know some samples? You remember the empirical distribution? So how does it look like? 1 over n and a summation of what? Of delta functions, each of them concentrated on each of the samples. You remember? So if you put this delta function there, right, do you agree with me that you're going to get 1 over n, the summation over little n, and then you're going to have this function here, because this is multiplied with delta functions and integral, will be this argument calculated at each of the data points xn. You remember when you have a function f of x multiply with delta of x minus x0, you get f of x0, okay? So here what we have is, we have the KL distance, really the distance of Q from the empirical distribution of P, because P is not known. It comes out to be this nice expression. So here is the nice argument that it seems to come up in many, many papers in machine learning, in deep learning, etc. If you're interested to find an approximation of Q, which minimizes the distance of Q from the empirical approximation of P, this is equivalent. There's a minus sign here, all right? Well, if you are going to have an approximation of Q, right, and let's say the Q approximation is a Gaussian, you're going to have some unknowns in that Gaussian, and let's call these unknowns like mean and variance theta. That's why you see this theta on Q, all right? So Q are the parameters in the distribution Q that you're going to try to fit so that you minimize this distance. So it comes to minimize this distance is the same as maximizing, if you get rid of the sign, this summation here. And what is this summation? So a summation basically of the logs of Q calculated at this point x of n. And obviously the samples are independent, right, identically drawn from this distribution. But what is this? It is the log likelihood, okay? So it comes out that minimizing the distance of Q from the empirical distribution of P is the same as maximizing the log likelihood of Q. I mean, really the data drawn from P, but you know, you are going, because you don't know P, here you maximize the likelihood using the approximate distribution key. So obviously, right, if let's say P is, so the question is, what if the two distributions are different? For example, if P has two modes and Q is a Gaussian with one mode, then this will give you garbage. And that's why you have to be very, very careful what type of approximations you look to the various distributions you have. So for example, if this is bimodal, and you approximate it with a Gaussian, effectively what you do is you approximate one of the modes of the multimodal distribution, not the other modes. Okay? So you have, certainly you have to test exactly the way you're going to do this and be sure that if you use parametric representations for Q, you need to be sure that sort of they belong to the same type of families that P is. Okay. So this is very important, and we may use it again, right? But I will talk a little bit more about maximal likelihood today, if time allows. All right, a few more definitions, and we're out of information theory. So what I want to define is the conditional entropy of y given x. So basically is, if x is given and you observe y, all right, how much information that gives you, all right? So if x is already given, you know, having an observation of y, what information it adds, okay? And you notice I circle this to indicate that even though here we use the conditional distribution of y given x in the definition of entropy, you notice this is the joint distribution. You need this for the calculations basically to fit nicely together. Actually, if you don't want to remember this, you can remember this derived result from there. It takes basically 0 time to show this, and it's a common sense result, and it says that the joint entropy of x and y is the entropy of y given x plus the entropy of x. That makes sense, right? I mean, is, you know, you say if I knew x, what information y brings, that's this entropy. And of course, because you don't know x, in here on the left side, you say plus the entropy of x. Okay? And of course, you can write this symmetrically as the entropy of x given y plus entropy of y. There is a very nice proof that I'm giving you here, right? That we actually, let me see if I can, okay, I cannot. If we only look at the title, it says if we have a discrete variables, and somebody tells you that the entropy of y given x is 0, just from intuition, what does that possibly mean? Don't read the rest of the slide. Okay, I don't want you to be polluted by math. But if somebody tells you that the entropy of y given x is 0, what do you expect that to imply? For just a discrete variable. In other words, observing x brings you 0 knowledge about y. So what do you think that means? You know what? You remember your voice doesn't come in the recording, and if I cannot hear, I cannot even repeat it. So someone has to tell me loudly so I can repeat it. So what does h of y given x means? Equal to 0. So knowing, if I know what X, observing Y doesn't bring any information, basically. What does that mean? That Y is really some function of X. All right? It doesn't contain anything beyond what X is. It's some function of X. Okay? And the proof is actually given on this slide just to confirm this common sense result. All right. Now, an extremely important definition, extremely useful for this course. I heard somebody said, the previous definition of X of Y given X means independence. Well, here is a nice definition of independence. You remember up to now we talked about a measure of variables being uncorrelated. What's the variable? What do we use for uncorrelated variables? What's sort of the measure we use to call two variables uncorrelated? The covariance or the correlation coefficient, normalized covariance, okay? Well, uncorrelated doesn't imply independence as we talked. So if you really want a measure of independence, that measure is what is called mutual information. Okay? And mutual information, you remember if X and Y are independent, P of X and Y is equal to P of X times P of Y. So a nice definition of mutual information is basically the KL distance of the joint distribution from the product of the two marginals. Right? And so when you talk about independence, this is what you need to use. Okay? So if the mutual information is 0, then you can claim that X and Y are independent. Let me just, there is really no derivations to be done because following the definition of the definitions also of the entropy and relative entropy, you can show lots of very simple results. So let's forget the mathematics. We know what this is, so it's basically definition of independence. So the mutual information, it says here, is equal to the entropy of Y minus the entropy of Y given X. So if this is 0, do you really agree that the entropy of Y should be the same as the entropy of Y given X? Basically, the idea is if they're independent and I observe X, it brings 0 information about Y. So this has to be equal to H of Y. Okay? I mean, just common sense, and it basically follows directly from this definition. Again, this identity on the bottom is symmetric, so you can write it the other way around like this. And there is a graphic representation, I don't know from which of the books is, but basically, you can derive all possible equalities between this mutual information and the relative entropy and the joint entropy. And you can look in the notes. Most of these definitions are sort of, these identities are common sense. Okay. All right. There is a recent development. I'm going to finish with this. I'm going to only give you, the flavor of this development. For very complicated distributions, it's very difficult to find the mutual information, right? Because you remember there is an integral there, the distributions are very high dimensional, it's very difficult to perform. So people are trying to come up with something better for defining the independence of random variables. And I think I mentioned even on lecture 1, it is basically an unsolved problem. If you have very high dimensional distributions, saying are they independent, you really don't know. We don't have an efficient algorithm that can check independence of high dimensional random variables. But in an effort to come up with new ideas and more useful techniques, it has been introduced as what is called a pointwise mutual information, where we measure basically, this is the log of P of X, P of Y, divided P of X and Y, where X and Y, they're not distribution, they're not the distributions, they are pointwise events. So basically this calculation, that's why it says pointwise mutual information, you evaluate it at each possible values of X and Y, which imply doing sort of a kernel estimation-like calculation. You split your domain of x and your domain of y in bins, and in each bin you do this type of calculation. Now you may say, if I split in bins, that has the issue of the Kirchhoff dimensionality, so this calculation would be also very difficult to do in high dimensions, indeed. But somehow it comes out that you can discover interesting independence relations that otherwise you will fail to do with classical techniques. So, pointwise mutual information, you remember the mutual information, the way we defined it before, it was the average of this with respect to p of xy. You remember this integral we had before? So effectively, if I take the average of this, I get the mutual information. But these guys, and I'm going to give you the key reference, they suggested that we define what is called a pointwise mutual information. And then they went to define the final entity that they call maximal information coefficient, which looks this very strange, very nasty sort of equation. What does it say? Let's say if you have two variables, x and y, discretize the domains of x and y in bins, and let's say the size of these bins is x times y. So maybe 5 bins in x direction, y, maybe 10 bins, and compute the pointwise, how do we define the pointwise information, the pointwise mutual information on those bins, on every location, and then take the maximum of those values, divide it by the log of the minimum of x and y. Okay? So when they do that, they call this maximal information coefficient, and they even take it a little bit further by repeating this calculation for many different discretizations of the domains of x and y. So they take different sizes bins, and then with some constraints on the number of bins they use in x and y, they compute from repeated calculations of this what is called the maximum information coefficient. Very weird, but this paper made it in the Science magazine, and is claimed in many, many papers as being sort of the future way of figuring out independence between high-dimensional variables. So it has received sort of lots of buzz in the literature, and their paper is basically a 2-page paper, and the buzz comes from the results they obtain. So they show, and I'm not going to go to details, they show that when this mutual, the maximal coefficient of, what's the word we use, maximal information coefficient, it is high, even if the correlation coefficient is very small, it implies strong nonlinear relations between variables. And an example is given by this data set, realistic data sets, and the plot shows the correlation coefficient versus this maximum information criterion, and you notice here the correlation coefficient is small, but the mixed score is very high. And when you look actually how the data sets behave, you get very strong nonlinear relations that all of the existing measures of independence fail to capture. Okay? So if any of you wants to know about independence, you certainly need to go and visit and read this paper. It's only 3 pages long, all right, and it has received a few thousand citations because obviously it's a big advancement in this area. Okay, we already have discussed this. I wanted to summarize some of the things we saw with inequalities. Can somebody summarize for me the equation on the bottom, what this equation says with words? Which, as we said, is applicable for any distribution. We will use this for proving convergence of Monte Carlo simulations. So what is the equation on the bottom say with words? the probability of x of being away from what? From the mean of x by distance epsilon times the standard deviation is less than 1 over epsilon squared. So the probability of x being away from the mean by 2 times the standard deviation is less than 1/4. Universal formula regardless of the distribution. Okay? Then we talk about the law of large numbers, and we gave 2 versions of it, the weak and the strong forms. And so what these 2 equations basically say, that as n goes to infinity, I should have used here a capital N, to follow the notation we had before, but it's okay. So as n goes to infinity, what happens? What is this x n bar? The sample mean approach is basically with probability 1 the actual mean of the distribution. Okay? And in a similar setting, basically, if you want to see the central limit theorem, the sample mean, it comes out to be a Gaussian distribution with mean, the exact mean of the distribution, and a variance sigma squared over n. Okay? So if you take samples, you form the sample mean and you keep repeating this, what you will get is a Gaussian. And it doesn't matter from where the samples come from. They can come from a beta distribution, from a Cauchy distribution, whatever. When you take the sample mean, as n goes to infinity, you basically get a Gaussian. Sigma squared over n will give you the error in the approximations that you do to the mean, so this is very useful. So let me do one example, and you will read the rest on this, because it's a very simple example, but it's it's an example that it comes in many textbooks basically. So you maybe have not seen a Poisson process before, a Poisson distribution, right? So it's a counting distribution. So let's say you count the number of cars passing an intersection in time t, and you say, the number of cars, the probability of the number of cars in time t to be n is given by this distribution, where lambda is a parameter that we use in the Poisson distribution. So what I want to do is, I want to show you that using the central limit theorem, I can approximate a Poisson distribution very well with a Gaussian distribution. I mean, you will never think that a Gaussian distribution can be an approximation of a counting process like a Poisson distribution, but actually you can use a Gaussian approximation, and sometimes you will not even know the difference. Okay? So the calculations are trivial in the slides as an application of the CLT theorem. But let me simplify first. I'm going to fix the time. So I'm going to count up to time capital T, and I'm going to call lambda t to be a parameter theta. So this is my Poisson distribution. So n follows, again, I see a typo there. If I use n, little n there, I should make this a little n. Okay? So this is a Poisson distribution that looks like that. Do you know what's the mean and the variance of Poisson? I mean, you can prove it in a few seconds, but what's the mean and the variance? Huh? 1 over theta? Okay, theta. So both the mean and the variance come up to be equal to theta. Okay. So I'm giving you a derivation actually here, and maybe I will highlight it very fast, okay? That I can approximate a Poisson distribution with a Gaussian with mean theta and a variance theta. Sounds very weird, right? You have a Gaussian where the mean and the variance are the same. Well, I mean, if you really want an approximation to the Poisson distribution, this is the Gaussian that does it. And the proof is actually, I'm going to highlight, and there is a little 3-page paper that you may want to consult, you can show that a variable, a Poisson variable, can be written as the sum of any independent Poisson variables coming from a Poisson distribution with parameter theta over n. Okay? I don't prove this, but it's given in this little document. It's basically a few lines of derivation. But you can show again that a Poisson random variable is the sum of n Poisson random variables coming from this distribution where the parameter theta is theta over n. All right? Theta there, theta over n. So, central limit theorem in action, where you don't think it would be useful. If you form the sample mean, all right, of this sample xi coming from this Poisson distribution with parameter theta over n, then you get a Gaussian with a mean theta over n, and the variance, you remember, sigma square over n, which is theta over n squared. Can you see that? So, I did not give you the proof, right, but we said a sample from a Poisson with parameter theta is the sum of n samples from this Poisson. So, but the sum of this divided by n, according to the central limit theorem, has to be Gaussian with the mean of this, and a variance here, sigma square over n. Sigma square is theta over n, because the Poisson has variance theta over n, divided by another n, theta over n squared. So x, which is the sum of xi, will be n times this variable, and that comes to be a Gaussian that has a mean theta and a variance theta. So here's a plot of how a Gaussian distribution using the central limit theorem approximations looks to be a very good approximation of a Poisson distribution, especially when theta is high value. Okay? And to take it even further, you can actually, what you can do is you can plot the KL distance between the Poisson distribution and the Gaussian distribution, and you can see that after some values of the mean, the KL distance becomes really of the order of 10 to the minus 2, 10 to the minus 3. So if you want to do calculations with a counting process like a Poisson process, you can even do these calculations with a Gaussian, and that's why Gaussian distributions are sort of very useful. Okay. I have to figure out if I should cover this topic or not, but let me ask the following question. If I give you a number of samples that come from one distribution, and you can think of this being a scalar variable, and I ask you, are these samples coming from a Gaussian or not? What test would you think you'll be able to do? You know, go back to your computer and say, okay, I'm going to test if something is a Gaussian or not. What will you do? What? Huh? But how do you define the, you mentioned that, okay, we have to compute a residual, okay? Residual means of the samples from, how do you define that residual? No, well, I don't tell you what distribution, I give you the samples and I'm asking you, do they come from a Gaussian distribution? That's what I'm asking. I know you have. Or t-test, okay. You are getting too complicated for me. I was looking for something very simple. So, I mean, a very trivial thing someone can do, right, is, okay, you give me the samples. I can compute the sample mean, the sample variance, write down a Gaussian, and start drawing lots of samples from that Gaussian. If they look following the distribution of the samples that I started with, then you can say it's Gaussian, right? So now another way to do this, if you look at the equal probability contours of a Gaussian, how do they look like? So let's say, if I had a Gaussian on the plane, x and y, how are the equal probability contours look like? What do you get? Think of the Gaussian e to the minus x minus mu transpose sigma minus 1 x minus mu. We will give you the calculation shortly, but how do the contours of equal probability Gaussians look like? They're ellipses, all right. So, can you use the concept that these equal probability contours are ellipses to figure out if a Gaussian sample, if a sample is a Gaussian sample? Can you compute, so if I give you an ellipse, right, can you compute what's the probability mass of that ellipse for a Gaussian? Right, so if I draw, a contour, an ellipse, not an arbitrary one, but corresponding to the covariance matrix, can you compute what's the probability of you having a sample inside that ellipse? I mean, in principle, can we do that? If the answer is yes, then you start drawing lots of samples, all right, from once you form the empirical mean and an empirical covariance, and you form a Gaussian process, a Gaussian distribution, you can start taking samples from that, and then you can see how many samples are in a given ellipse that has a given defined probability. If you don't get that, then basically your samples don't come from a Gaussian. So what I do is in the next slides, I give you sort of, I want you to go and read it, okay? But effectively what I do is I plot this equal probability contours, okay? And I compute how this ellipsis will look like for a given probability inside this contours. So let's say if you want an ellipse where the probability being inside that ellipse is 50%, I can compute that exactly, all right? So then I can start drawing samples from this Gaussian distribution that I formed, and if 50% of those samples are not inside that ellipse, then I'm not Gaussian. And so there is a little exercise that shows you a sample that is Gaussian, it works nicely, but also shows you a sample that is certainly non-Gaussian, right? So you can see the samples looking like that. There's no way you can fit this to a Gaussian, okay? And even though when you do a calculation, you will see that the sample mean and the variance of these data points, all right, they don't look bad, all right? But the actual samples that come from a Gaussian distribution with the empirical mean and variance, they basically don't look anything at all like what you see here. Okay, so if you read the calculations, we will compute exactly this equal probability ellipses, and we do effectively a calculation that shows the following diagram. All right, we take ellipses that correspond basically to a probability mass that goes from 0 to 1, and then we compute the number of samples that come up to be inside those ellipses, and this equation that you see here, the relation between the probability P to be inside, let's say, an ellipse that has 50% probability mass, has to give you 50% of the data points you have to be inside that. And you can see the deviation between a Gaussian sample and non-Gaussian sample, it is obvious. Okay, so this is a very good way to compute, at least in low dimensions, if a sample corresponds to a Gaussian distribution or not. Okay, we don't need this. I'm going to bypass as a simple example. There is a proof that the multivariate Gaussian in the notes has maximum entropy. You can read that. You may say, do I really care about these derivations? Well, you do. You know what? Because they involve lots of basic calculations with Gaussians that may come in a sort of a different context, but the calculations may be almost identical to what you see on these proofs on maximum entropy, for example. All right, so let me go to the MLE estimate, and we will do this formally. We have a univariate Gaussian. This is what it is. And somebody gives us samples of X. And we want to find the best estimates of mu and sigma squared. And the best estimates of mu and sigma squared are the estimates that maximize the likelihood, the evidence of the data. Right? So we assume that these data are IID coming from this underlying Gaussian. Right? And we will find mu and sigma squared that maximize what we call the likelihood function. Attention now. This, you notice in the definition, right, the samples come, let's say, from this distribution, but I call this a likelihood function, and I imply that their function, it's a function of what? So when I write the likelihood function, given like that, I imply function of what? The distribution parameters, mu and sigma squared. So don't think of the likelihood as a probability distribution. Think of it as a function of the parameters. Okay? So for example, often we're not even going to bother to normalize this or anything like that, right? It is a function of the parameters. We need the parts of this probability that relate to mu and sigma squared, all right? So because this is what we need to optimize. Because the samples xi are independent from this distribution, I can write this as the product of these univariate Gaussians computed at xi, all right? So this together gives me a function of mu and sigma squared, and I want to find the estimate of mu and sigma squared that maximizes the likelihood. So working with likelihood in general is it's messy because, let's say, Gaussian has mu and sigma squared in the exponential, so you don't want to have to deal with exponential. So the way to do this is to work with the log likelihood. So the maximum likelihood estimation is basically maximizing the log likelihood of the data. And so when you take logs, the product becomes summation, and the optimization problem looks like that. Okay? So I am not going to go through the one-line calculation, but I trust you can take derivatives with respect to mu, set them to 0, take derivatives with respect to sigma squared. That's easier than taking derivatives with respect to sigma, set it to 0, and here's what you get. You basically get a result already used even from lecture 1, that the maximum likelihood estimates are the sample mean and the sample variance. And it comes out the sample variance is the variance with respect to the sample mean. All right, because we don't know the exact mean, so this is what it comes out about. So this, we will see it makes this estimator a biased estimator, and we underestimate basically the calculation of the variance because of this term here. So, okay. So let's look at these expressions on the top. This x comes from a data distribution, let's say that it's a Gaussian. So will you agree with me that these estimates of the maximum likelihood estimates are also random variables? Right? I mean, I use 50, let's say, samples of x, but each of them is a sample from a random variable, so they're random. They come from a distribution. So mu is random and sigma squared is random. So can we compute the expectation of mu and the expectation of sigma squared? And so I'm claiming, yes, I can. And these are what the values are coming. And to derive this, I am using these two identities. So you have to help me from where these two equations come from. From where is the equation on the top coming? It says E of xi xj equal to mu squared for I different than j. What is implied here? If I is not equal to j, the expectation of xi xj is mu squared. Mu is the exact mean of the distribution. Where's this mu squared? This is the result of what assumption we are making. I and j are independent, so E of xi xj is E of xi times E of xj, which is mu squared. And if I and j are the same, this is the second moment of xi, which is the variance plus the mean square. Okay? So when you expand those expressions there and you take the mean, you come up that the mean of the MLE estimate for the mean is the exact mean. So this is an unbiased estimate, but you notice the variance is underestimated. Okay? This doesn't come up to be sigma squared, it's n minus 1 over n, but not a big deal if n equal to goes to infinity or n is large, but theoretically speaking, it is not equal to sigma squared. All right. Can you correct the variance for and get an estimate that is unbiased? Well, it's very simple, right? So if instead of using the sample mean for the variance, you use 1 over n minus 1 times the same summation as before, this estimate, of course, is unbiased. All right. So let me ask you, we have a few minutes, will you be able to do this calculation for a multivariate Gaussian? And I want you to learn how to do this because these calculations with multivariate Gaussians can be a pain unless you can do the algebra fast and unless you know where to look for formulas you may need. So what I'm doing here is I'm expanding the log of a multivariate Gaussian. Looks like that. All right, so you notice this is the degrees of freedom. All right. I have n samples. From the exponential, the product of the probabilities basically will give me a summation over these expressions. And I want to optimize this with respect to the vector mu, and I want to optimize this with respect to the symmetric matrix sigma. Will you be able to do derivatives with respect to mu and sigma? Obviously, I mean, immediately you can see, okay, mu maybe is not a problem, all right, but you can see sigma, you have the log of a determinant of sigma, so you're going to have to differentiate the log of, well, in the simplest form, right, you have to take the derivatives of the determinant of the matrix with respect to the matrix. Is that a problem? Well, it will be a problem unless you study the underlying formulas for derivatives with respect to vectors and matrices. Here you have to take a derivatives of this with respect to sigma, or the way I do it in the notes, I take derivatives with respect to sigma minus 1 to make the calculation easier. And actually, there is a complication sort of when you try to find the MLE estimate for sigma. Sigma is asymmetric. What guarantees do we have that if we take derivatives with respect to sigma that the result will come to be symmetric? Right? I mean, why should it come the derivative with respect to sigma to be symmetric? So someone will say, well, maybe I need to enforce some Lagrange multiplier, something that says that this matrix is symmetric. Which actually in a matrix form I have to think how you may do that because I don't really, it doesn't come up from anywhere. Right? So by accident, if you take derivatives with respect to sigma, it comes out that the MLE estimate for sigma is symmetric, so you are safe. Okay? But in general, we don't know that to be the case. So what do you need? Let me give you the answers. The answer is not surprising, is the MLE estimate for mu is the sample mean. The MLE estimate for sigma is the sample covariance, right? Exactly as in the univariate case. And you need two identities basically to be able to do these derivations. And these identities are coming very often in this calculation. So if you have the trace of A, B, where A and B are matrices, derivative with respect to A, you get B transpose, and the derivative of the log of a matrix with respect to the matrix is A minus transpose. Those who have taken courses in continuum mechanics in engineering most probably will be able to identify these relations, but I trust from the fact that there are 2 students annually taking that course, most probably have never seen these derivations before. Okay? But sort of they're coming up everywhere in the continuum world, so there's identities you should be able to familiarize yourselves. So here's a trick. And I wanted to show you this trick because we will need to use it in follow-up calculations later in this course. So let's say I want to take the derivative of this term, the last term, with respect, rather than differentiating with respect to sigma, I'm going to differentiate this with respect to sigma minus 1 because it will make the algebra easy. So let's compute the derivative of this with respect to sigma minus 1. So look what I have done. I took this summation and I wrote it as such. And I would like you to help me why this summation is equal to that summation where I see there is an operator outside that says trace. This is a universal trick that you will use in every lecture effectively starting, Wednesday. Why this summation that comes up in Gaussians, multivariate Gaussians, I can write this as the trace of sigma minus 1 over n, okay, n and n cancel out, but I write this as 1 over n of x n minus mu, x n minus mu transpose. Can you help me? How do I get this? What type of quantity is this summation? Is it a scalar, a vector? What is it? If it is a scalar, can I write that this quantity is equal to the trace of the same identical quantity? Nice. If you have a trace of A times B, do you know the identity that is the same as the trace of B times A? Try it with matrices. Trace of AB is trace of BA. So if that is the case, then what have I done here to move sigma minus 1 outside? If trace of AB is the same as trace of BA, I move this xn minus mu where? To the left. And then there was a sigma minus 1. And what have I done to sigma minus 1? I move it to the left, and because it doesn't depend on little n, I move it outside. And what is 1 over n xn minus mu transpose summation over n? Is the scattered data matrix centralized? I mean, every operation in machine learning, right, starts by centralizing the data and forming this scattered data matrix, this covariance matrix that you see here, all right, this symmetric matrix. So I can write this trace of sigma minus 1 s, where s is given, and then you can use this formula here to differentiate, and the answer basically comes to be immediate, that our MLE estimates are the ones that you see here. Okay, I was told that the class is recorded for 2 extra minutes, so let me see if I can tell you anything intelligent in 2 extra minutes. Okay, so here is something, and maybe we will continue this on Wednesday because it's very important. If you have a problem with big data and you want to compute the MLE estimate because it's an important point estimate, you want to do it as data arrive one at a time. You're not going to go and sum all the data and then somebody sends you another data and do another calculation, right? You want to compute this sequentially, and nicely enough, if you do the algebra, it comes out that if you know the MLE estimate for n-1 data set, and a new data point comes, yes, you can update your MLE sequentially. And for those who work on stochastic optimization, deep learning and things like that, this looks like a learning rate, right? So you compute basically the error as the new data point arrives, and then you use that learning rate and the error to improve your estimate. Now, this is an exact calculation, but it comes out you can do this same calculation using ideas from stochastic optimization, and that's the Robbins-Monro algorithm that I will discuss on Wednesday. And it is an algorithm that computes the 0 point of a noisy function. Okay? And does anybody in the audience, except the ones that I know the answer, has seen this before in any other problem? The Robbins-Monro? Basically, let me just say that 90% of stochastic optimization methods in deep learning, they're basically really extensions of the Robbins-Monro algorithm that looks trivial because it's empirical sort of, but it always works. So if you have a function, but you only know this function with noisy data sets, it allows you to find the zero of that function on an iterative process that looks like this, with some constraints on this learning rates that satisfy these equations. So we will do this for the MLE estimate, and we will see more use of the Robbins-Monro algorithm in forthcoming lectures. So I will come up on this topic on Wednesday. See you then.